So today will be a really short one. We're going to be talking about tautologies and contradictions. So what are tautologies and what are contradictions? What do I mean by them in a logical sense here? A tautology is a statement that is always true, while a contradiction is a statement that is always false. Now, I want to stress what I mean by always in both of these definitions. What I mean by always is that in any possible scenario, in any possible universe that you can dream up of, a tautology is always true and a contradiction is always false. Like, it doesn't matter which timeline you come from, whenever you say a statement which is a tautology, nobody can say that you're lying because you're always going to be telling the truth. And when you're talking about a contradiction, it doesn't matter which timeline you come from. I can always say that you're lying, that what you're saying is always false. Now, when I say the phrase every possible universe, your mind should automatically be thinking about truth tables, because I said earlier that a truth table can tell us things about every possible universe. So yeah, we're going to be discovering several tautologies and several different examples of contradictions within a truth table that we are going to construct. So how would that look like? What are we looking for? Okay, so if I have a truth table over here with some statements, it doesn't matter what they are, then a tautology will look like this. It's going to be true in every single possible row, while a contradiction is going to look like this. It's going to become false in every possible row. So that's equivalent to what a tautology should be and what a contradiction should be. Each row corresponds to a different universe. So if it is true on every possible row, then it is true on every possible universe. So this is what we're going to be looking for when we are constructing our truth table. So let's check some examples out. Let me invent a symbol P, and I'm not going to give it a meaning because it doesn't matter what the symbols mean when we are constructing a truth table, because the symbols and what they stand for, they don't affect how we should make the truth table in any way whatsoever. So we have a symbol P. Well, P can be either true or it can be either false, right? That's all the possibilities there are. It's either true or it's either false. It can't really be anything else. Like, those are the only two options. Let me also add a symbol not P. So this is pretty familiar to you all. If we have P and not P, then what this symbol does is it just flips the original statement here. So if we have T, then we have F, and we have F, then we have T. So I'm going to remind you, why can't we add TP and why can't we add FF? Why is this universe not a possibility and this universe also not a possibility? Well, it's because how can, in one universe, how can it be that P is true and P is not true at the same time? Because this statement says that, oh, P is true, but not P is also true. And how can something be true and not true at the same time? And similarly, how can something be false and not false at the same time? It's just something that breaks logic. So you can't have these kinds of universes. It just can't logically exist. So these are the only possibilities that we should be concerned about. Next, I want to add another statement here. I'm going to add P. This is or, so it's P or not P. And let's fill in the entries for that. So since this is an or statement, only one of P or not P needs to be satisfied. In other words, only one of them needs to be true. Well, in both universes that we have here, we have at least one of them being true, right? So it satisfies the necessary conditions. So it's true on all possible realities. And there we have it. That's our first example of a tautology. P or not P. And let's continue on with an example of a contradiction. It's actually pretty similar. We just have to flip the or sign with an and sign and not P. So since this is an and, this means that both conditions need to be satisfied. Both P and not P need to be true in order for this thing over here to be true. But P and not P, like I said earlier, it can't be possible that PP is a universe, like that universe doesn't exist. It can't logically exist. So this should be F, F, because none of these are both true. Only one of them is, and that's not good enough. So, since this is F on all possible universes, this is a contradiction, and this is a tautology. Now, you might not exactly be convinced because, well, really, how can a statement be true in all possible universes? How can it be possible? And how can a statement be false in all possible universes? Like, surely that can't be true because there are so many possibilities. But how is it possible that this statement is always true and this statement is always false? Well, let's try to give an explanation to that. So the best way to do it is to convert this thing into English, just because we can't really understand it right now. So let's give P a meaning this time, and we give a meaning just so we can translate it, so we can understand it better, not because it is necessary or not because like it fits into our truth table some way or somehow. It's just for clarification purposes, okay? Meaning doesn't actually mean anything. And that statement sounded paradoxical, but yeah, meaning doesn't mean anything because the meaning of P isn't going to change how we're going to make a truth table, okay? So I just want to express that a lot because it's really important. So we give a meaning P. Let's use a same example from a previous video. We're going to say P as Peter goes to Starbucks. So how do we convert this into the English language? So Peter goes to Starbucks. I'm just gonna write P. P goes to Starbucks, or P does not go to Starbucks. Does not go to Starbucks. So whenever you say this sentence here, no matter what universe you are in, this will always be true. And if you think about it, well, yeah, it makes sense. Like you walk up to a person and they say, well, Peter, he might have gone to Starbucks, or he might not have. And when he says that sentence, sure, it doesn't give you any information at all. It's completely useless. But what he's telling you, logically, what he's saying is the truth. Now, similarly, let's try to translate the next thing here, our next example, a contradiction. So this translates into Peter goes to Starbucks and does not go to Starbucks. So, how is it possible that you are doing something and not doing something at the same time? How can Peter be going to Starbucks and also not going at the same time, right? So it doesn't matter what universe you are in. If you say this sentence out loud, it's always going to be a lie because it's impossible for it to be true. And the only way for this to be true is if we just break logic entirely. But then what would be the point of this video series if we try to do that? we set the rules of logic to function in this way. So it should be true that it's impossible for a person to be doing something and not doing something at the same time. So right now, I'm just going to repeat this again. I'm terribly, terribly sorry, but the meaning of P does not matter. You can set P as Peter writes a book. So Peter writes a book and does not write a book at the same time. That statement will still become a contradiction. So the meaning that we assign to P doesn't really matter. It doesn't affect anything. This will always be a contradiction regardless of the meaning that you assign to it. So I just like to stress this out. Meaning does not matter, and it's really important when we're considering studying logic and truth tables and all that kind of stuff. So tautologies and contradictions are also useful in set theory, which was something that we dabbled in the previous video. But before we get into that, I want to teach you one more thing about sets that I left out in the previous video. If we have set, just a really simple one, then, well, you know what this set means, right? But let's take a look at X here. I said that X literally means any mathematical object. So basically, we have a warehouse of mathematical objects here, and we are cherry picking the ones that satisfy the condition. So there's this huge warehouse that are filled with mathematical objects, shapes, vectors, matrices, numbers, like complex numbers or something else, just any mathematical object. And we're just cherry picking the ones that are even, right? But if you think about it, it's terribly inefficient because, like, when you're talking about evenness, like over here, if your statement is talking about being even, then why should you bother checking shapes? Like, shapes can't be even or odd, I think, maybe. Like, yeah, shapes can't be even or odd. Decimals like 0.5, like that can't be even or odd. So why are you wasting your time to check these objects? You only need to check one object in particular, and those are numbers, right? So any mathematical object, there's a smaller branch over here that is talking about numbers specifically, and you only want to be cherry picking from this tree, I guess. You only want to be taking stuff from this part of the warehouse, and you don't need to be concerned with this part because, well, it's a given. These things can't possibly be even. We only know of even numbers. There's no even anything else. Okay? That's what we're talking about. So we only want to be dealing with this specific part over here. And we call this specific part a universe of discourse. So the universe of discourse for this set is numbers, because that is the universe in which we are cherry picking our mathematical objects from. This is the universe where our X comes from. Remember, X means any mathematical object. By that, we narrow it down a bit. We specifically mean numbers. So X comes from a universe full of numbers, and we are cherry picking from that universe those which are even, those which satisfy any condition. So let me give you a different example. Maybe we could have 2D, okay? So X such that X is 2D, two-dimensional. So what is two-dimensional? Well, shapes are two-dimensional, so you only have to be dealing with shapes. So this is your universe of discourse. You're only going to be cherry picking shapes which are two-dimensionals. So whilst you are walking through this universe, you want to be cherry picking the squares, the triangles, the circles, and all that other stuff, and you want to fit them all into this set. Well, earlier last video, we talked about this set X such that Px, and if we have Y attached to it like this, then this will be equivalent to saying Py, right? I hope you still remember. Now, let's say that P here, we put it in the truth table and we figure out that it's a tautology, so it's true in all possible universes. What does that mean for this set and this statement in general? So if it's a tautology, that means the statement is true for every single possibility out there. That means that if we have a specific universe that we are cherry picking from, like, I don't know, numbers basically, we're cherry picking from numbers, that is our universe of discourse for this example. And if P of X is true for every single possibility, every single universe that you can think of, then you don't have to cherry pick because P of X is true regardless of anything. Like a meteor could strike the earth and destroy it, and this P of X will still always be true. You could have a universe where math doesn't exist and this is still going to be true. You know, it doesn't matter, okay? So you can literally pick anything from the universe of discourse and this will always be true. So you don't have to cherry pick at all, really. So inside your set, we have everything, basically everything inside the universe of discourse. UOD. So your set here, we can put absolutely anything inside of it because this is true regardless of anything. So our set contains the entirety of our universe of discourse because we don't need to cherry pick at all. There is no condition we need to satisfy because the condition is already satisfied. It is a tautology. We don't need to check. We don't need to think it's true in all possible cases. Now, what if P of X is a contradiction? That means it's always false regardless of anything, regardless of which universe you are in. It's always going to be false. So what do we do now? What happens now? Well, any number that you put inside, it isn't going to satisfy P to the X because P to the X over here is a statement which can never be true. You go into this cherry forest and you can't pick any cherries at all because none of those cherries like satisfy the statement because it's impossible for the statement to be satisfied. So what do you end up with in this case? What happens when P to the X is a contradiction? You end up with a set that is empty. This is known as the empty set. So there's absolutely nothing inside of it. And this is different from saying 0 is inside of the set because 0 is something, okay? This is the empty set. It contains absolute nothingness at all. And since it's stupid to write an empty set like this, okay? What is this? Like, I don't know. It's a really weird symbol. Just a bracket, just an open bracket and a closed bracket. We use a different symbol to call it. So we have an O and we put a dash through it. This is an empty set. This is how we call it instead of just randomly placing an open bracket and a closed bracket. And that's it for the video. Thanks for watching.